Yes, yes. Can you hear me too? Can you hear me? Okay, okay, good. Thank you very much. So thank you, Marcia, for your very kind introduction. And thank you, everyone, for inviting me and for attending my presentation today. So the work I'm going to present is in collaboration with Samer Abdullah, Ingsun, Hatem Taif, and David Keys, all at KAUST. And the slides that I'm going to present are available on my website. So if you go to that website, you will find a link. It's called SINAPE, and you can download the slides if you wish. As you can see here, there are 74 slides. I'm not going to go over all of them, but the deck is complete on the website. And so if you're interested to read more and some of the finer details, then you're welcome to download the slides and take a look. So what I'm going to talk about today is an overview of an attempt to do large-scale spatial data science with a software that we've been developing over the past 5 years now at KAUST called ExaGeoStat. So ExaGeoStat stands for exascale geostatistics or spatial statistics, which means doing spatial statistics at very large scales on supercomputers, but also on your laptop if you wish. So that's the topic that I will cover today. Before I do that, I would like first to tell you why I would enjoy coming back to Brazil again very much. As Marcia said, my first trip to Brazil was about 20 years ago. And it was just after the regression school that we went to Rio. It was carnival time. And Beatriz Mendes at UFRJ organized for us to join Samba School, Villa Isabel. And you can recognize on the picture, I'm here with my Chilean friend, Reynaldo Arellano Valle, Wilfredo Palma, and Pilar, who sadly passed away soon after that. So it was a very memorable time when we went dancing in the Sambódromo. And so this is something I will never forget. I came back to Brazil about 10 times over the years. And I really would like to come back. But here's why I cannot enjoy Caipirinha with you this year, unfortunately. I would like also very much. The latest son, he's just 3.5 months old, and it was just not possible to fly to Brazil this time. Okay, so my talk is going to have 3 parts. The first part will give a very brief overview of some concept of spatial statistics that I will be investigating with this software. So to give some broad overview about that. Then in a second part, I will talk a bit about high performance computing, or HPC, to give you some ideas about that field and how they can help us for this particular problem, but maybe more generally also for statistical computing. And the third part is about an R version of ExaGeoStat called ExaGeoStat R. So there I will also give you some information. There is some code also. I won't go over the code, but you can use if you're interested to play with that software. So the talk will really be in these three parts. So just to motivate a bit the type of problem that we'll be considering here. So we're going to look at spatial data, data located in a geographical region in space. Here we're considering wind speed in Saudi Arabia in June 2010. Those are hourly data. Each row here corresponds to a different time. And these are the data that are observed, for example, at 28 stations in Saudi Arabia. So here you have Saudi Arabia, and this circle represents these 28 stations. And each circle is colored according to a color scale that tells you the amount of wind in terms of speed. And what we would like to do is, based on these observations, to be able to predict the wind speed in the whole country. So to come up with a predicted mean here, so basically a predicted map over Saudi Arabia that will tell us the wind speed at location where we have not observed this data. And then also we'll be able to simulate realization from the model to give predicted quantile at 5% or 95% and so on. So this data set is really spatial temporal, so it evolves through time. I will mainly in the talk focus on the spatial case, so just look at one time point and how we could do spatial interpolation between observation, essentially. Now, imagine that instead of 28 stations, you have 1,000 or 100,000 or even 1,000,000 locations. Then how can you do this kind of spatial interpolation? This is what we'll be talking about in this presentation. If you want to read more about this particular data, here's the source reference for that. So we'll be considering very simple Gaussian random fields, so basically Gaussian processes with mean 0. So we'll not focus on the mean here, but instead we'll focus on the dependent structure that we'll model with a Matern covariance function, which is quite popular. It's described here. It says that the covariance of the variable of interest, for example, the wind speed z at two locations in space, Si and Sj, is given by this formula. It involves the distance between the two locations Si and Sj, so the norm of the difference. K here is a modified Bessel function of the second kind of order nu. Gamma is a gamma function, and 1 is an indicator. This quantity tau square here is often called the nugget. If it's different from 0, it represents small scale variability. If it's different from 0, the variance of the process would be sigma square plus tau square. The parameter nu controls the smoothness of the random field of its realization. And the range beta controls the rate of decay of that covariance function as a function of distance in space. So eventually what we want to do is to learn or estimate these 4 parameters in the covariance function. And it's useful to talk about the notion of effective range. So this function here, when the distance between the location becomes very big, goes to infinity, that function goes to 0. So the covariance and the correlation go to 0. So it's the range, if you want, the distance at which the covariance become exactly 0 is infinite, but it's useful to talk about an effective range. That would be the distance at which the correlation function in this Matern model, for example, reaches a small value, let's say 5% of correlation. If you have data on a unit square, you could say that the spatial dependence is, for example, weak if this effective range is 0.1 compared to the unit square, medium if it's 0.3, and strong if it's 0.7. So 0.7 would mean that if you take any point in the unit square, it's only at distance 0.7 in that unit square that the correlation has decayed down to 5%. So here are some plots of different submodels of this family of Mattern covariance function. The first one is called the exponential correlation. In fact, it's just exponential of minus the distance. This is obtained when this parameter nu equals 1/2. This is called the Whittle correlation function when nu equals 1. This is a Mattern with nu equal 1.5. And when nu goes to infinity, we obtain what is called the square exponential, or sometimes the Gaussian correlation model, although the field can be non-Gaussian, but it's basically exponential of minus the square of the distance. In each plot, you have three curves. So as a function of the distance h, the distance separating any two locations, you have three curves, green representing weak spatial dependence, blue representing medium, and red representing strong spatial dependence. And this means that those curves, so here horizontally, I have a dotted curve at 5%. This means that the green curve for the weak case, we said it crossed 5% at the distance of 0.1, the blue crosses at 0.3, and the red crosses at 0.7 for strong dependence. And this is the same for all four plots. But what is different is the behavior at the origin. If you compare this one here, the correlation leaves the value of 1 very straight down, whereas for this one, for example, you see the behavior is more kind of tangential departure from 1. This behavior at the origin is what will dictate the smoothness of the random field. And so now we can look at realization. So here I have 4 different submodels of the Mattern covariance function, each with 3 types of spatial dependence, weak, medium, and strong. And therefore I have 3 times 4, I have 12 different submodels, if you wish. And here I have plotted realization from each of these 12 models. So the first column represents the case of the smoothness equal to 0.5, 1, 1.5, and infinity. So this is basically the exponential. The first column is the exponential covariance, and the last one is the square exponential, which is popular in machine learning, for example. And you can see when you increase nu, this parameter, the realization become more and more smooth. So these are very smooth compared to the exponential that is quite rough. The different rows correspond to different level of dependence. So first row is weak dependence, second medium, and the third strong dependence. So for example, you see very well in this case here when you have, so the value are color coded here, they have mean 0. So you see the groups of red and blue groups are compact and short in distance, whereas here you have very strong dependence in this case. So you have a very strong region of red, for example, of high values, and here there would be a pretty big region also of bluish values. So these are different realizations. And essentially, if you have a number of observations from that random field, you don't observe it completely in the unit square, then you want to estimate these parameters. So typically, what one would do in a Gaussian case is to use a likelihood approach. So you have just one realization from the spatial random field. We assume it has mean 0. You could model the mean separately. And if you have n locations, so n observation in space, the log likelihood function would take this familiar form that just comes from the multivariate normal distribution, where the vector z appearing here in this quadratic form is the variable of interest observed at the n location, S1 to Sn. And sigma is a covariance matrix that is of dimension n by n, and again, the number of locations. And if we use this Matern model, it will be parameterized by this vector theta of parameters that we're trying to estimate. Now, this log likelihood function involves the log of the determinant of sigma, and there's this inverse of sigma in this quadratic form. So basically, when n becomes big, exact computation becomes very difficult with this Gaussian likelihood. So you basically, typically, you would compute a Cholesky factorization of that matrix sigma, and this would require order of n cube floating point operations and order n square memory. And when n becomes big, then this becomes very difficult to handle. Then you would maximize the likelihood or minimize this quantity here with respect to theta to obtain the MLE. Of course, there are other approaches to estimate the different parameters. One of them is to do least square fitting of the parametric model, so the Matern model. And here's an experiment that just demonstrates why this type of empirical fitting are not so good. We consider the simple case of an exponential covariance function, or if you take 1 minus the exponential, again, h is the distance in space, 1 minus the exponential is what is sometimes called a variogram, so that's the exponential variogram. Assume that there's only one parameter theta controlling the range, the rate of decay, and the true value is 0.25. So we consider a Gaussian process, GP, with mean 0 and with this exponential variogram. We're going to generate 400 random locations in the unit square and a realization of that Gaussian process at those 400 locations. And based on this 400 observations, so n equals 400 here, we estimate theta either by ordinary or weighted least square. So essentially, you estimate this variogram quantity empirically, and you fit the model by least square, either without weight or with weights. And we compare this with maximum likelihood under Gaussianity. So we have 3 methods to estimate theta, and we do this 1,000 times. So for each method, we have 1,000 estimate of theta. And if you plug them into this variogram curve, a function of distance, you have 1,000 such curves for each of the 3 approaches. And then we use the functional box plot to summarize this information. The true underlying variogram for this value of theta is represented by the green curve here. I'm not sure if you can see it very well, but it's here. It's the same in all 3 cases. And then we see the variabilities of the different estimate of the curve. So you can see that going from ordinary to weighted least square, having some weights, you can reduce a bit the variability. So this magenta region is the box of the classical box plot, if you wish. But you can see that with the MLE, this box in magenta is much narrower, so the variability is much smaller as we would expect. So this is why doing maximum likelihood is much better. And in fact, we have, if you want to read more, we have done some experiment beyond this very toy example where you have more parameters and more scenarios, and also under non-Gaussianity to kind of see how robust this Gaussian process fitting is, and in general is still advantageous to use a likelihood-based method. So this is why we focus on likelihood method, on Gaussian mainly, but we have also some non-Gaussian model implemented. So once we have estimated this parameter theta and we want to do predictions, the so-called kriging, predicting at a new location where we don't have observation. So Z is the vector of dimension n where we have our n observation. Now we want to predict Z at a new location S0 where we have no observation. If we assume that we have a Gaussian random field, any realization will be multivariate normal here of dimension n plus 1. And basically the optimal prediction that is unbiased and minimize the mean square prediction error is the conditional mean of the Gaussian. So here we find again the covariance matrix for a vector of n observations, so of dimension n by n. And we need to say, once we have the model, what's the covariance between S0 and any of the n locations. So that's this vector k here. And of course, we need the covariance at, or the variance in this case, at the new location S0. So the conditional distribution in the Gaussian case is very well known. So Z at S0, given the n observation in the vector Z, this is the conditional mean, and this is the conditional covariance matrix. And so you can, or here, because we're predicting at just one new location at a time, that matrix actually of dimension 1 by 1 is a conditional variance. So you can use the conditional mean for prediction, and you can also have a measure of uncertainty with this conditional variance. Here again, you need to find a solution of a linear equation that involves sigma inverse. And so you need a Cholesky factorization of the matrix sigma. So as I mentioned before, if you have n location, it's very costly to do Gaussian likelihood, exact Gaussian likelihood estimation, and also the kriging, the spatial prediction. So what we're trying to do here is to use high performance computing to deal with the case where n becomes large. And this is the motivation to basically build this software called ExaGeoStat. Of course, in the literature, there are many approximation methods that have been proposed to reduce this computational problem. So you can approximate the covariance matrix in some way, or approximate the likelihood in some way, and so on. There are many, many proposals. But the problem with this proposal is that they are not really compared extensively with some benchmark data set, because it's just very difficult to have large data set and kind of figure out what would be exact solution in those cases, because they are difficult. So this is why with this software, we started to launch a competition at KAUST on spatial statistics for large data set. The first one was in 2021. And so with the software, we were able to simulate exact realization from very large Gaussian random field. And then we can fit also exactly the Gaussian likelihood for these large random field, these realizations when n is quite large. And then basically anyone with approximation method could try the method on this data set and see how close they come from the exact solution and how it works. So that was the idea behind this competition. The results have been discussed, analyzed, and summarized in this paper. If you want to read a little bit more about it, I will tell you some main ideas linked to this competition. So we launched it in November 23 of 2020, and it ended on February 1st of last year. There were 29 research teams from all over the world who signed up, who registered, and 21 of them eventually submitted results. The competition had 4 parts, 1A, 1B, 2A, 2B. The competition 1 was based on Gaussian process models. The part A was about Gaussian process estimation of parameter of a Matern model, and the part B was about prediction. The data size was 90,000 observation here for estimation, and then predicting at new 10,000 locations. And part B was with some non-Gaussian features through this so-called Tukey GNH random field. And so here was a case where we had 90,000 for observation for training and 10 for prediction. And in 2B, they were much bigger. We had 900,000 location and 100,000 for prediction. The metric that we use for the Gaussian process parameter estimation were a mean loss of efficiency and mean misspecification of the mean squared error. So essentially, if you use an approximate method, it's as if you're using an approximate covariance function. and you can quantify, since we know from which model the data were generated, we can quantify the loss that comes from these approximations. And for prediction, we simply use a root mean square prediction errors. So the top winners in each of the competition, they use different type of approaches. Some use some kind of composite likelihood or Vecchia approximation or some other method. And you see from one competition to the other, there were different groups that succeeded with different type of method, and it depended also a bit on the analysis that they were doing on the data sets. Just to tell you a little bit more about the Gaussian case. So of course we ran also ExaGeoStat, but we didn't compete with the others. This is why we are out of rank. But these are essentially the scores that the teams would get. If you do the exact estimation with ExaGeoStat, then your score will be better here than any of the other competitors. If then you do prediction, prediction with the true model got the best score, but you see that if you do the estimation of this parameter and then the prediction, you see here we were very close to the best method. So there can be some tiny difference. And there were some other group that used some other technique to do the ranking. And also in the non-Gaussian case, it was more difficult. And there were quite a few groups with different methods that came up tied in the ranking. So just to summarize a bit what we learned from this competition, we understood better when each of these approximation methods became inadequate and when it worked and when it didn't. The data set that were generated, so 1 million observation in space, are publicly available. You can download them at this address here. They can be used as benchmark for future research. So if anyone comes with a new method to do large-scale spatial statistics, that method can be applied to this benchmark data set. And there we have the exact result from maximum likelihood and from predictions. By Kriging, they can be compared. One can see the rank of that new proposal among the other in the competition and so on. Also, the result from these different groups, they are publicly available on our website. So all this information is already there. This year in 2022, we launched a second competition. There we tried some deviation by using non-stationary data in the mean and the covariance. We had spatial and temporal data as well, and some bivariate random field. This year there were 20 teams that signed up, and 15 of them submitted their result. The winners have already been announced, and we're doing some analysis of the result, and those will be shared pretty soon. Okay, so that was the first part where I kind of give an overview of the kind of problem that we're interested in and the kind of problem that we're trying to solve. And the second part is a bit about high performance computing, or HPC, and how we can use exascale computing tools for spatial statistics. So first, why do we need high performance computing? Basically, there's more and more demand because of the flood of data. So here's an example for the year 2020. Daily, so per day, the average internet user, for example, generates 1.5 gigabyte of traffic. And many other connected situation will generate a lot of data. If you have a factory and it's connected, it could generate up to a million GB per day. So this is very big. And you have, so high performance computing tries to address setting where you have this large amount of data. And you will find, if you look at the typical workload of HPC problem, they come from astrophysics, bioinformatics, AI, finance, weather and climate, which is the kind of application that I'm interested in, and cybersecurity. So just to tell you a little bit more about, eventually I'm going to talk about supercomputer. Of course, we're interested in parallel computing, where basically you have a shared memory. We have several processors, they share the same memory, but something that can be better is to distribute the computing. So each processor will have its own memory and can do computation, and then you need communication between these different units, and this is what typically is on a supercomputer. So what is high-performance computing? It's basically the use of parallel processing to run advanced application programs, and you want to do this efficiently, reliably, and very quickly. And this is to solve problems that are either too large for standard computers or take too long. And so the type of problem that I described, they will go to that direction when the number of locations becomes large, then basically it's very difficult to do computation, at least exact computation on standard computers. So this high performance computing system, typically they have compute nodes, and even just one of them might be much better, much more powerful than a typical personal computer. They often have multiple processors. So for instance, the supercomputer at KAUST has 2 processors on each node, and then each will have many cores. So the one at KAUST has 16 cores on each of the processors. So this means 32 cores per node. And then there are around 6,000 nodes on the supercomputer at KAUST, for instance, and this leads to around 200,000 cores eventually. And you may also have sometimes accelerators such as GPUs. So HPC, typically, this term is used when this computing system, they function above 1 teraflops, which means of the order 10 to the power 12 floating point operation per second. So this is already pretty fast if you think about it. And if we want to talk about exascale, exaflops is 10 to the power 18 operation per second. So 10 to the power 18 is a very big number. It's 1 billion operation. So both with B, 1 billion operation per second is a very big number. And in fact, the top supercomputer up to this June, the fastest were operating at petascale. And it's only now recently since June that the first exascale supercomputer has been launched. It's in the US. I'll talk about it just in a little bit. What we'll have been playing with is the Japanese Fugaku supercomputer. So this supercomputer was the most powerful in the world until June of this year. Now it's ranked number 2. So Fugaku doesn't reach exascale, it reaches 537.2 petaflops per second. And it has 7.6 million cores. So you see it's a very big machine. You can see the picture here representing Fugaku. Fugaku means the mountain Fuji in Japan. And if you look at the slide, you can click, there's a virtual tour. It's quite nice. You can look through the supercomputer, the different rows here. It's a very big machine, a very costly machine also to have. And this supercomputer, you can think about it as if you have 20 million smartphones, you put them in a room to do computation, or you have 300,000 standard server in a single room to do computation. So it's a very, very powerful machine. So the first exascale computer now is in the US at Oak Ridge National Lab. So it reaches 1,685 petaflops, at least theoretical peak. So this means 1.6 exascale. Fugaku is number 2 now. And there are some others. I listed some here just to give you some ideas. So number 4 is Summit, also at Oak Ridge. And there are many from different countries. I found also that in Brazil, you have one called Dragão, which I guess means dragon. And no surprise, this is with Petroleo Brasileiro. So that's a pretty good supercomputer. At KAUST, we have Shaheen 2, which 5 or 6 years ago when it was purchased was number 1 in the Middle East and number 7 worldwide. But you see that very quickly those toys become outdated. And now it's ranked number 97. It has 7 petaflops, so you can see the difference between this one and Frontier, for example. Okay, so now let me tell you a little bit more about the motivation, basically to use HPC for geospatial statistics. A discussion with Dorrit Hammerling at the National Center for Atmospheric Research in July 2019. She said, increasing amounts of data are being produced. So for example, by remote sensing instruments like satellites and numerical models, climate models. But technique to handle millions of observations have historically lagged behind. Computational implementation that work with irregularly spaced observations are still rare. Of course, if you have data on grids, you can use tricks such as fast Fourier transform and the like. When the locations are irregularly spaced, then it's a bit more difficult. So if you think about a matrix that would be of dimension 1 million by 1 million in double precision, that would require about 8 terabytes of storage. And in terms of computation, n cube is already 10 to the power 18 flops. So traditional approaches to come up with approximation are either to use low rank method globally on the matrix, so diagonal plus low rank, for example, or covariance tapering, so setting some outer diagonal entries to 0. But these are still fairly rough approximation. There are better approaches. For example, hierarchical low rank approximation, where you divide the matrix into different tiles and you can approximate the different tiles with different low rank approximation depending on the need. And also another idea is to reduce the precision of how you store certain entries in the matrix that you consider. So let me just move to tell you about the different components of ExaGeoStat. Essentially, it has 3 main parts. One is a data generator. So basically, you can simulate from Gaussian random field and now also from non-Gaussian one at very large scale. So for n, very, very big. And you can create benchmark data set, as I showed you for the competition that we launched. There's a component about maximum likelihood in the Gaussian case, but now also in some non-Gaussian models. So we can fit, for example, the Matern correlation function for data that are very large. And there we can do exact, so what we call full matrix is basically without any approximation of the covariance matrix sigma. And one approximation that we have currently implemented in the version officially available is called tile low rank. So that's exactly this method that divides the covariance matrix in different tiles and does some approximation on each tile. I'll show you an example just in a little bit. And the third component is about prediction, about kriging. So we predict a variable of interest at new location based on the model estimated by maximum likelihood. So that the basic 3 components, but now we have added not only univariate Gaussian cases, but we have also some multivariate models, some space-time models. We have this non-Gaussian model with 2pGH transformations, and we have also some non-stationary model that we have implemented. Okay. To tell you a little bit more about the structure of the software, I mean, eventually here at the top, you have the application from climate or weather, environmental science. We try to do modeling, inference, prediction. There's an optimization library, an LOPT, for optimization of the likelihood. We need some parallel linear algebra libraries that work on that are very optimized for different platforms, but also for high performance computing. So dense computation are based on this library, Chameleon. And the tile low rank computation, this type of approximation with tile, is based on HICMA, which is a library developed here at KAUST by the Extreme Computing Research Center. And then we have what is called a dynamic runtime system. So the different tasks essentially will be done in parallel, but different tasks take different times. So you need, for example, here for a Cholesky factorization, a DAG that will control the different tasks applied on the different tiles and see how to assign them to the different processors and so on. And the software has been built in such a way that it can run on shared memory system and distributed memory systems. We can run it on a supercomputing computer. You can run it on a cluster of machine on your desktop or even on your laptop. It can basically you can ask the software to use CPUs or GPUs, depending on what you have on your machine, and it will take care of that. You don't need to code or do some special complicated adaptation when you go from one computer to the other. So this portability is very important in our view. This means that it can run on many different platforms with many different type of CPUs or GPUs on different computers, including different supercomputers. So we've run on all of these. So the portability of the software is one of the strengths also of that software. Okay, I will not talk in detail about that, but I wanted to tell you about the representation of the covariance matrix in ExaGeoStat. So essentially that big covariance matrix is going to be split in different tiles. We only need to store the diagonal and the lower part because of symmetry. So you see it's divided into different tiles, and each tile, for example, in the exact computation is stored in double precision. So DP is double precision. You could do, for example, this kind of approximation. It's called here diagonal supertile, but it's also basically tapering, where some of the tile you set exactly to 0. This one here is what is called tile low rank approximation. So you keep some tiles in double precision without approximation, but some of the tiles here are approximated with a low rank approximation. So a product of two matrices with lower rank here, K, and this K can change from one tile to the other. So it can adapt with different region of the matrix, can have different type of approximation. Then the other type of approximation is to think about different precision approximation. So in this case, this part here in blue is stored in double precision, but the part in gray is stored in single precision. Or even this case, you have double, single, and even half precision for the part in red. And of course, you can combine these ideas. This is what Jacques Dongara called responsibly reckless matrix algorithm for high performance computing. So Jacques Dongara is at Oak Ridge and is the recipient of the Turing Award this year. And basically the idea is to approximate as much as possible, so in somewhat reckless way, but still be responsible. So control that eventually the output that you get are in certain level of precision that are tolerable for the application that you have in mind. So in this first figure here, these are mixed precision with dense computation. So again, the tiles are either dense double precision, here dense double or single, double, single, and half precision. And you could also imagine that you mix those. So you don't have just a band, but you kind of, for each tile, you decide what's the best precision that it should store in. In this figure here, now you can combine mixed precision and this tile rank approximation. So in this case, the diagonal of tiles is dense double precision. This lower part is double precision, but with tile rank approximations. You could have a band of dense and this tile rank. You could have this diagonal dense double precision. The gray, so all these are tile rank approximation, but the gray are in double precision and the blue are in single precision. And of course, you could do more. So you could mix double, single, and half precision here in dense. And here you could mix double and single precision in tile rank, for example. So these are all kind of approximation that can be used in this software. Okay, so just wanted to mention here where you can find the software ExaGeoStat. So we have a GitHub for ExaGeoStat, and there is another version for ExaGeoStat R, the R version. So you can access those. There have been different releases, and there should be a new release in a few weeks about the very latest version that we have. Okay, I've listed also here the publication that are related to this software, because many of them are in IEEE journal on parallel and distributed systems, so not the typical kind of statistical journal, although we have some. There's the one about the competition also. So if you want to read more, it's all there. And our latest paper has been accepted for the supercomputing conference in November 22. In fact, it has been selected as one of the 6 finalists for the Gordon Bell Prize, which is a very prestigious prize in HPC. It will be very difficult to get the prize, unfortunately, I think, because Fugaku is a very difficult supercomputer to run on. I mean, it's a little bit like if you drive a Ferrari, you know, you might have a lot of power, but there's a lot of fine tuning to be able to drive it smoothly and according to some procedure. But still, that was very nice recognition from this HPC conference. So the last part here is about ExaGeoStat R. So I will just say a few words. Essentially, on top of ExaGeoStat, we have an R wrapper that allows to call ExaGeoStat from R and do some operation from within R. So for statistician, it's much easier to use. And so here I have a lot of code and comments. I will skip those. I'll let you read if you want to read a bit more, but I'll just make a few comments. So we've done some comparison in terms of speedups of ExaGeoStat R and some typical and popular R packages to do spatial statistics, namely GeoR and fields. And in this plot here on the left, you have execution time per iteration in the likelihood in seconds. The blue one is GeoR, the green one is fields, and the red one is ExaGeoStat R. So you see that ExaGeoStat R is quite a bit faster. And also these two, essentially, they will stop at around n equal 20,000 location. With ExaGeoStat R, we can go much further here, about 70,000 location or so. And in this plot is basically the ratio of execution time. So in blue, the ratio between GeoR and ExaGeoStat R, and in red, between fields and ExaGeoStat R. You see that ExaGeoStat R is about 30 times faster than fields and about 100 times faster than GeoR when you start to go into large problem sizes. Then you can, ExaGeoStat R, you can also run on different system. Here is run on heterogeneous system where you have CPUs and GPUs. So as a function of the number of locations, here again you have execution time per iteration. The purple is with 28 CPUs, and then the other one are with 1, 2, or 4 GPUs. And in small dimension, doesn't make too much difference, but once you reach larger dimension, like 100,000 here, then you can see quite some significant improvements if you have a bunch of GPUs for that. These are results on a supercomputer now, on Shaheen 2, the one at KAUST. And horizontally, you have number of location in thousands, so this reaches 250,000, and with different number of nodes, 4, 16, 32, 64, and 256, and you see the kind of improvements that you can get. And finally, this plot is about running on Fugaku, the Japanese supercomputer, and these are now matrix sizes in the millions with different number of nodes, or also different type of approximation. So the red one is the dense one, and then you can either have mixed precision with dense or mixed precision with some Taylor rank approximation. The very last one run that we got last July, this past July on Fugaku, is running on almost 11 million size matrices. Okay. So to summarize, I will use this timeline of the development of ExaGeoStat. So we started in 2017. That was the first year when we started on this project. So we released a version of ExaGeoStat and the R version as well to do large-scale spatial data science. It was basically generating large data set, exact modeling with Gaussian likelihood and predictions. So these were all exact. In 2018, we started to build this Taylor rank approximation. So we released 2 new versions, and they supported this Taylor rank approximation through this HICMA library developed at KAUST. In 2019, we started to go into mixed precision. At the beginning, there were just 2 levels, so double and single precision. In 2020 was the COVID year, but we still released a new version using a runtime system from the UTK group called Parsec. And there we could do also 3-level mixed precision, so double, single, and half precision. 2021, we launched this competition, spatial statistics for large data sets. We had a workshop also with NVIDIA. We had a competition there as well. We built the space-time model. We have also a parallel optimization version of the likelihood with an algorithm called P1. So not just kind of single optimization, but this can be parallelized as well. And we introduce also some non-Gaussian model. And in this non-Gaussian model, we have in exact and TLR form, but another type of approximation of H matrices or hierarchical matrices called Hodler. And finally, this year, there will be a new release pretty soon coming up. We had a second competition, and we also introduced this benchmarking function to assess different modeling performance of different packages. And we're exploring this a bit further. So thank you very much for your attention, and I'll be happy to take any question that you may have. Thank you very much.
Thanks, Marc, for a very nice presentation. Perguntas?
Thank you for your talk. I really appreciate that. I don't have really a question, just a side comment. The Brazil oil company has a new supercomputer.
Okay.
It's called Pegasus. It can reach at, I think it's 63 petaflops.
Okay, very good.
So you might want to update your list.
Yes, thank you very much. My list is based on the top 500 websites. So this is a website that officially record the top supercomputer of the world. Not everyone or every country wants to register the supercomputer there necessarily. To register it, you need also to provide some proof of the performance. So I think you have to do some experiments and provide some logs of the speeds and all that. So I know that maybe some countries haven't submitted all their supercomputer there, but thanks for letting me know. Yeah, that's great.
You have access to Fugaku. We don't have access to any other supercomputer from Petrobras.
Yes.
So,
yeah.
Unfortunately.
Yeah, sure. But of course, not everyone has access to a supercomputer, and you don't necessarily need, I mean, to do experiment at very large scale. And of course, if you want to see how it works on a computer that, for example, has exascale capability, then you would have to try to run on Frontier. But the software can run also on your laptop, on your desktop. So you don't need a supercomputer to necessarily do some experiment yourself.
Well, thank you.
Thank you.
Renato?
Hey, hi, Marc. Thanks for the talk. As you increase the number of stations, the number of points, probably you also have a lot of nonlinearities, I mean, regimes that only occur locally. So in a way, there is a trade-off, because as you get larger and larger data sets, you also would need some more local models for those specific regions that have a different. So in a way, you could break the problem and look only of the data for the local region. So how do you think about this kind of trade-off, or how do you approach that, especially on your with your examples here with very large data sets in your matrix, your low rank tile approximation, for example?
Yeah, thanks, Renato. This is a very good question indeed. So, I mean, I don't believe that just stationary isotropic Gaussian model for very large size is kind of the best model, but it's one of the building blocks of many other model, non-stationary model, or using them locally and so on. So we're expanding the software to build new capabilities, but some of the fundamental one we're trying to establish now. I know you've done work in spatial statistics for large data set with subsampling and ideas like that. There are many of these ideas that can be implemented and explored further. But if this fundamental operation you can do very fast and at very large scale, then they can be useful in many other settings where, as you said, you have non-stationarities. I mean, you have many data on very large scale, then it's very natural that you have non-stationarities in the mean and in the covariance function and so on. And so stationary isotropic model are just a building block of these more complex models.
More questions? I have one not technical question. If one student from here wants to work with you, your group, what he or she should do? Can you say some words about that?
Well, send me an email. And eventually, I mean, there's a
scholarship or something like that?
Yes, so all students come with full scholarship at KAUST. They don't pay tuition. Of course, they are selected. There's on the KAUST website, they can apply. The application is free. There's no fee for that. And actually, I believe there is a student from USP coming this month to work with my colleague Howard Rowe. So we have a couple of Brazilian students and postdocs as well. Actually, I have one.
Okay, thanks. One more question.
Thank you very much for the excellent talk. Would you see a role for developing sampling methods that actually help you to break down the larger problems into smaller problems that then can be where the modeling after you've done for the smaller sets could be combined to produce better predictions?
Yes, thanks for the question. Absolutely. I think Renato has done some work in that direction, and there's more work going on. I have a visiting student currently who has been looking at how to subsample, where to take the location of observation in a subset to basically achieve optimal rates of prediction as if you would have the whole data set. So ideas like that definitely are of interest and can be pursued. Yes.
Mais perguntas? No? So let's thank Marc again for a very nice talk. Thanks, Marc.
Thank you very much. Thanks. Bye-bye, then.
Bom dia a todo mundo. Antes da gente encerrar o evento, eu queria anunciar os prêmios de melhor iniciação, dissertação e tese aqui do SINAPE, tá? Eu vou subir aqui para eu ir chamando as pessoas com o resultado aqui. Bom, então eu vou começar com o prêmio de iniciação científica e vou de trás para frente para dar uma emoçãozinha, né? Em terceiro lugar foi o trabalho do Anderson de Oliveira da Fonseca. Por favor, se ele estiver aí. Não, esse é o de doutorado. Pode subir aqui que eu vou te dar. É um segundo, porque esse aqui é o de doutorado. Esse aqui. É de iniciação. É esse? Então. Um segundo. Calma. Vou te dar o certificado. Parabéns.
Obrigado.
Depois tem um prêmio em dinheiro, eu vou pegar seu Pix e te falo o valor. Tá?
Beleza.
E te transfiro. Bom, agora eu estou com certos aqui. Em segundo lugar, também da Federal da Bahia, o Jonathan Souza Pimentel. Parabéns. É melhor a gente sair aqui de trás. Depois também tem um prêmio de dinheiro, eu vou pegar seu Pix para te transferir, tá bom? Bom, e talvez seja surpresa para todo mundo, menos para o ganhador agora, né? Em primeiro lugar, Fernando José Monteiro de Araújo, da Federal de Santa Maria. Tá bom. Então ela vai receber aqui em nome dele o livro do Pedro também, como prêmio, tá? Vamos tirar foto também, você está recebendo, vai. Continuando para o prêmio de dissertação, deixa eu já pegar aqui para não ter confusão. Isso. Vamos lá. Então, o prêmio de dissertação, a comissão não conseguiu achar um terceiro e um segundo lugar, então existe um empate no segundo lugar, tá? O Matheus Maia, da UFBA, e a Áurea, da Unicamp. Bom, o Matheus não estava aqui, né? Parabéns. Tudo bom. Tem um prêmio em dinheiro também, depois eu vou pedir seu Pix para transferir, tá bom? Bom, e aí, em primeiro lugar, o Vinícius Soares, da USP. Também o livro do professor Pedro com Júlio. Parabéns. Obrigado. Seu certificado. Tem um prêmio de dinheiro, aí depois eu vou pegar seu transferir, tá bom? Obrigado. Boa sorte. Parabéns. Obrigado. Bom, e por fim, o prêmio de doutorado. Agora deixa eu pegar lá de novo. Vamos lá. Então, em terceiro lugar, foi o Guido Moreira, da UFRJ. Por sorte, os nossos palestrantes doutorados estão todos fora, menos o Guilherme, né, que está aqui. Então, ele não pôde receber. O Guido está em Portugal. Em segundo lugar, foi Guilherme Lopes, da UFMG. Se o galo não está dando alegria, você se garante, né? Depois eu vou pegar seu Pix, tá? Bom, e em primeiro lugar, o Rodney Vasconcelos, da Unicamp, que está em Israel. A Luiz, você quer receber para ele aqui? Seu orientador. Bom, então. Matheus. O Anderson podia também receber para o Matheus, né? Vai ser. Bom, parabéns pela sua orientação. Aqui o livro e o certificado. Obrigado. Então, eu vou aproveitar e utilizar que o Anderson está aqui também para ele receber o prêmio do Matheus, que foi o segundo colocado do mestrado. Tá? A gente vai mandar virtual também. Tampa a bandeira do Brasil. Bom, gente, então estamos chegando ao final de mais um SINAPE. Eu queria agradecer a todos vocês por todo esse tempo, pelas conversas, pela paciência. Eu queria agradecer enormemente a organização local, em nome do Flávio, da Patrícia, as meninas, os professores, todos envolvidos na organização. Eu tenho certeza que foi um ótimo SINAPE, foi muito bem organizado e é tudo crédito deles mesmo, tá? Eles só me mandavam WhatsApp e eu só dava ok. Foi muito fácil nesse sentido. Pode, claro, desse jeito ficou ótimo. Então, para mim, foi muito bom trabalhar com eles, de verdade. Agradecer a minha diretoria, a Larissa e o Celso também, porque esses 2 anos foram intensos e aos poucos vai chegando ao fim. Desejar sorte à próxima diretoria, que vai se candidatar, vai ter candidatos, espero, estamos aqui, estou contando com isso. Tá? Agradecer a Luana também por todo o trabalho, esforço, tudo que ela faz. Tá? Merece, né? Os nossos técnicos ali, ó, que ajudaram a gente durante toda a conferência, todo mundo já deve estar familiarizado com a cara deles. Muito obrigado por tudo também. E assim, declaramos encerrado mais um SINAPE, agradecendo a todos os participantes mais uma vez. Parabéns.